Good morning, good evening, good afternoon, wherever you may be watching this from. And my name is Cornelius Lubinda. Continuing on addition mathematics vectors. Now this is from where we ended. We are going to now just continue from components of a vector. So, components of a vector. So here under components of a vector, what are we trying to say? Components of a vector, we can say something like, we have a vector, a certain vector. J, let me not say J, certain vector B. B is equal to 3, 4. So this is a column vector. When you do this column vector, it's just going to say you have moved 3 and you have moved 4. In the x direction, positive 3, you have moved 3 steps in the positive x-axis direction, and then 4 steps in the positive y-axis direction. That is what vector B means. Now, when we talk about components of a vector, we want to bring you to the I, and the J. So the I and J format. We can have our x-axis like this, and then our y-axis like that, making our x or y plane. So, for the I and J format, we're trying to say movement in the x-axis, or movement, you're moving along the x-axis. This 3 means that you moved like this, the positive x-axis. Then the 4 means you moved up like this. It doesn't necessarily mean that these are position vectors. It just means you moved like that, and you moved like that. Maybe you would have started from maybe a number like 5. You moved a 5 in the y-axis. A 5 here. Then you moved 4 steps up to find yourself 9. Maybe you started at a 4. You moved 3 steps to find yourself at 7. That's what you're trying to say. You moved this. And you moved that. So those movements, that's what we call, in the x-axis, we replace it with, because the difference here is 3. Now, this movement here, it is called the I. And then the movement up there, it is called the J, with a dot on top. So the I, the J there, and the I and the J. Now, just leaving them as I and J would be wrong, because it has not moved I. The magnitude of I. Which means we're trying to say I with bars. I. Magnitude of I is equal to 1. Magnitude of J is equal to 1. So, are we trying to say from 4 to 7 we have moved 1 unit? Honestly, no. 4 to 7 means 3I. 5 to 9 actually means 4J. 3I, 4J. So B, using the I and J, would be 3I plus 4J. That's where the I and J comes from. So, if you have not understood that part, we can repeat it once again. This time we won't choose any numbers, but we'll just keep this essential information. So we are saying movement in the x-axis is called I. Movement in the y-axis is J. I and J. The magnitude of I is 1. The magnitude of J is 1. These are what we call components of a vector, the I and J components. So as we move into additional mathematics, of course we are going to be representing vectors using the normal way, which is the column vector, and there are other ways of representing a vector, but we are also going to be doing this right here, representing them using the letters I and the letter J. So that is the components of a vector. Then the next thing that we need to know are, we can also so that's an example also, the angle made with the x-axis. The angle that a vector can make with the x-axis. So angle made with the x-axis. So angle made with the x-axis. That's the new thing. What are we trying to say? We can have a vector. Here so the angle that the vector makes with the x-axis, these are position vectors. We can have a vector that is going up like that to a certain point F. So upon us extending it to a certain point F, it means that here we can say this is 3, this is 1, this is 2, that is 3. Then this is 1, this is, we can just call it 2. Negative 1, negative 2. If we were to write this one in component form, and since it's a position vector, we just use the coordinates that are already there, which will give us F is equal to, we start with the X. In this case, the X is moving 1, 2. So we can start from, so here's the point here, but counting, don't start from the point. We count this as a 0, so 0, 1, 2. This is the negative direction, therefore it will be negative 2. Then here we move 1, 2, 3. 3. That is the vector. Now looking at the angle made with the x-axis, the reference point is the way quadrants are made up. So we know that we have several different quadrants. This is the first quadrant, second quadrant, third quadrant, fourth quadrant. Here we'll go like this. So the angle made is this entire thing, from there to there. Or, so, okay, let's just leave it like that. So this entire thing from there to there, it is our theta. Our theta. So having our theta like that, we can be asked, what is our theta when we have such a vector? Theta. So when you look at this, there is the trigonometric identities SOHCAHTOA. SOHCAHTOA. Sorry, I forgot an H. So SOHCAHTOA, it means the sine of the angle theta is equal to opposite over the hypotenuse. And then cosine of the angle theta is equal to the adjacent over the hypotenuse. Then tangent of the angle theta is equal to opposite over the adjacent. Now when you're asked about the angle made in the x-axis, always think about tangent. Tangent is the best. Don't think about the other two trigonometric identities, the sine theta and the cosine theta. So here, we have our tangent theta, opposite over adjacent. So this, we'll just carry it like this is the theta that they're looking for. So, but when solving, this theta that I told you about, it is to enlighten us. I'm just trying to say that in the question, they want you to find an angle that is in the second quadrant. It means it's between 180 and 90 degrees. It's an obtuse angle. They want you to find an obtuse angle here. This is why I extended this theta like that. But, hopefully you have followed me there. That's why I extended like that. They want an obtuse angle. From the first quadrant going to the second quadrant, this is an obtuse angle in total. But here, this is where people get very confused. Follow me very carefully. I hope I haven't lost anyone there. That's our theta. So what have I done? I've made the triangle. No, this is not any ordinary triangle. It is a right angle triangle. That's there. Representing a right angle triangle. That is where now we can use our Pythagorean identities. Here. We can use the Pythagorean theorem. Our trigonometric identities. Then now we can use our trigonometric identities here. So these are trig ratios. Let's just call them trig ratios. That's the correct way to say them. So the trigonometric ratios here. Okay, so we can forget about this theta. This was just to tell us that we need an obtuse angle, please. Do not confuse yourself. But the answer will be this from here to there. But we need to find this theta. I don't know if that makes sense. So this theta, what I've done, it should always touch the x-axis. So the theta should touch the x-axis. Now if you are to put your theta there, it's not going to touch the x-axis. X-axis to the hypotenuse. Always know that. This means we know it is our tangent theta. Tangent theta is equal to opposite over the adjacent. Tangent theta is equal to, the opposite in this case is positive 3. over the adjacent side, negative 2. Means tangent theta is equal to negative 3 over 2. Theta is equal to tangent inverse of 3 over 2. So we can ignore. We have seen the negative. The negative is just trying to tell us that we are not taking where tangent is positive. Tangent is positive in the first and the third quadrant. It is positive here and here. So this negative will come in handy. It means that we need to get our answer from the second quadrant or the fourth quadrant, because these two quadrants is where tangent is negative. So if we type tangent inverse, this is not in, make sure your calculator is not in radian mode. Tangent inverse of 3 divided by 2, which is giving us a 56.3 degrees rather. 56.3 degrees as our theta. Theta is equal to 56.3 degrees. So that is the theta here. Now I want to find the theta obtuse. Please don't get confused. Theta from here to there. To touch the vector here, this vector right here. This theta. So it means I'm going to say theta is equal to 180 degrees minus 56.3 degrees. So 180 degrees minus 56.3 degrees is, I think, 124.7 degrees. 124.7 degrees. That is your theta. That is the angle that this vector made, or the vector makes the x-axis. Alright, the last thing that we're going to look at is unit vectors. Then the next video, look at the scalar product of two vectors. So, we're now going to look at alright, I was just proof checking my answer. It's supposed to be 123.7 degrees. Sorry for that. 123.7 degrees. Let's look at unit vectors. Oh my goodness. Unit vectors. So we can have a vector A. The unit vector of A is represented by vector A hat. So it's a vector, then we put this hat symbol. That, like those hats where people stay. So A hat is the representation of a unit vector. We can have vector A hat like that. This is a unit vector. So how do you, if you're given a vector and then you're asked to find the unit vector, what do? Vector A is equal to, so we're going to use the Pythagorean identity, 3i plus 4j, like that. vector A hat is equal to this vector 3i plus 4j. You divide by the magnitude 3 squared plus 4 squared, 3i plus 4j, magnitudes. This is 9 plus 16. Vector A hat is equal to 3i plus 4j we divide by 25. You divide by 25. So this is a vector A hat. And then we can have a vector B. Vector B looking like this is equal to A I plus C J. And then we are asked to find the unit vector of vector B. So B hat is equal to AI plus CJ. We divide by A squared plus B squared. Plus C squared. So that's how we can do it. So AI plus CJ divided by A squared plus C squared, the square root. So to find the unit vector of a vector, it will just be the vector itself divided by its magnitude, like that. So magnitude is you get the x component to square it, y component to square it. You add them, then now you square root the answer. There, that will be your unit vector. So this has been Cornelius Lubinda with another presentation. Thank you for watching, and until then, bye bye.